Yeah, you can ask some questions. I was going to, let's see, still kind of waiting for people to get in. I guess we're recording. I'm going to start off with a question that was asked in the discussion board, and then I can take questions from people live. So the question from the discussion board is, Teodora Misick asks, when using the multiple regression model, is it better to take into consideration all possible independent variables that you can come up with, or is there an optimal number of those variables that give the best answer to the given question? So what she's asking here is basically, is there ever a downside to controlling for a variable? When we were working through the logic of multiple regression, we were talking about the importance of making ceteris paribus comparisons, holding all else equal. And so that language certainly implies that it can't really hurt to control for a variable. But in general, it actually can be dangerous to control for things. So when deciding whether or not you want to include a variable as a control variable, you should think about the difference between confounders as opposed to colliders. Okay, and what does this mean? So if you remember in one of the Q&A videos, this wasn't in the lecture, but we did a brief introduction to what are called directed acyclic graphs, which are ways of showing causal relationships between variables. And one directed acyclic graph we talked about was how if you had, just erased everything. All right, whatever. So again, we're talking about confounders as opposed to colliders. Okay, and for confounders, we can draw the relationship like this, where we have, this is education. This is income. Education causally affects income. All right, and in the lecture, we talked about how there's an omitted variable called ability. All right, and if we want to think about the direction that causality is going, ability causally affects the level of education you're able to get. It affects your grades, affects whether or not you can get into college, whether or not you can finish, stuff like that. And ability affects your income. You're a better worker, you get more promotions, stuff like that. Okay, and so we say ability is a confounding variable for the education-income causal relationship. All right, and if you have a confounder like this, where it causally affects both education and income, you ought to control for it in a multiple regression model. Okay, but there's another kind of relationship we can think about. All right, I'm gonna give an example here where we have looks, just how good looking are you, and acting talent. Okay, and there's no causal relationship between your looks and your acting talent, right? Anyone can be a good actor. Your ability to assume another persona has nothing to do with how good you look. Okay, so there's no causal relationship here. But let's say there's this third variable called being a movie star. And you being a movie star is causally dependent on your looks. Better looking people are more likely to be movie stars. And it's causally related to your acting talent. You have to be a good actor in order to be a movie star. Okay, and so notice that here, we have two causal relationships radiating out from ability. Here we have two causal relationships running into each other on our being a movie star variable. So that's why it's called a collider, because we have these two relationships colliding with each other. Okay, and if we condition on colliders, if we include them as control variables, then we can actually create relationships where there aren't any. Sorry, my daughter's, she doesn't like collider bias. It really upsets her. Okay, if we condition on colliders, if we include them as control variables, it can create problems. So for an example here, I have some constructed data. Let me share my stata. Hopefully you should be able to see that. Yeah. Okay. So we have variables for beauty and talent, and these are both just randomly distributed variables. So if we do scatter beauty talent, we can see that there's no relationship, right? And if we do a regression, if we do reg beauty talent, you know, we get a tiny, tiny coefficient and a big standard error. So she really hates collider bias. Basically, we can conclude. Sorry, this is a train wreck. We can conclude. We can conclude pretty definitively that there's no relationship between looks and talent. Okay, but then notice that I have this third variable here called star, and basically that's just a binary variable. So star equals 1 if your combined beauty and talent score is in the 85th percentile or higher. So basically, if you have above average combination of beauty and talent, then you get designated a movie star. Okay, so if we do a scatter plot of beauty and talent again, basically you can think that anyone that is above kind of this line here, these individuals here, are the movie stars in our sample, either people who are really good looking and okay actors, or people who are really great actors but not that good looking, and maybe some people who are both good looking and good actors. Okay, but let's see what happens if we control for that variable. Okay, so again, we're controlling for this variable that's about being a movie star. Look what happens to the coefficient on talent. We've gone from, you know, no relationship to a super strong, you know, negative 14 t-statistic negative relationship. And if we break it down, let's do a scatter plot of beauty and talent just for movie stars. And I mean, it's clear as day on the scatter plot, right? There's a negative relationship. And so this is why conditioning on a collider can be so dangerous. It can lead us to, you know, finding relationships between variables that aren't actually there. So in general, when we're thinking about should I control for this, should I not control for this, you need to think, is this variable a confounder, in which case you should control for it, or is it a collider, in which case you shouldn't control for it. So that's your general rule of thumb. And that we're going to talk more about that after the midterm. But that's a really good question. I'm glad it was asked. Okay, are there any other questions? Yeah, there's nothing else on the discussion board. So yeah, I'm happy to take your questions now. We can talk about yeah, stuff that you want clarification on before the midterm, or just clarifications about what's on the midterm. Yeah, so the floor's open. Yeah, you can go ahead. You can either type or go on your microphone, whatever you want.
Okay. I had some questions from the midterm review that was, well, I mean, the old midterm that you had posted. The first one is X and Y are causally related, and it was the reliable indications. And they were like, there was a list of, you know, a small, large p-value or something like that.
Yeah.
What was the correct one?
So, yeah, so here we're talking about, this is number 2 on the practice midterm. And it's basically asking which of the following tells you that X and Y have a causal relationship. So which of these can tell you that X causes Y? Okay, and so I think the options were, actually I have them here. So this we're asking, you know, does X cause Y if And so the first one is the covariance between X and Y is large. The second one is the correlation coefficient is close to -1 or 1. The second one is a large R squared, a large coefficient of determination, and then D is none of the above. Okay, so we can go through these. So the first one, if the covariance of X and Y is large, we can't even be sure that X and Y are correlated if that's the case, right? Because we learned that covariance is scale dependent. Like we can't tell just by looking at the covariance between X and Y whether or not they're closely related or not closely related. Remember, we could change the covariance just by changing the units of our observations. So if X and Y aren't, we can't even be sure about correlation from covariance, then we can eliminate that one. These two are more reliable measures of correlation, right? But that still doesn't mean that we necessarily have any causation. So you can think of tons of examples through the class of variables that are correlated but not causally related. Okay, so you can think about roosters crowing and the sun going up. Okay, the roosters crowing doesn't cause the sun to go up. It's actually the other way around. You can also look at, for a fun example, there's a whole website full of what are called spurious correlations. So here we have annual spending on space, science, and technology, and suicides by hanging, strangulation, and suffocation. And their correlation coefficient, and their R squared too, is really, really close to 1, right? But there's no reason to believe that these two variables are causally related, right? It doesn't really make sense why the US would spend more on space, and that would cause people to not only kill themselves more, but kill themselves more via hanging. Here's another one, number of people who drowned by falling into a pool, and the number of films Nicolas Cage appeared in per year. Again, here we've got a correlation of 66%, which is still pretty high. Again, very high correlation, pretty much impossible to argue causation. Per capita cheese consumption and the number of people who died by becoming tangled in their bed sheets. So yeah, and you can scroll through these, Age of Miss America and murders by steam vapors and hot objects. So, you know, the lesson here is correlation is not causation. So the correct answer to that one is D, none of the above. All of those are measures of association. There's no way for us to tell just by looking at them that there's any kind of causal relationship. We need more than that.
Awesome. Okay. The next one is which is an indication the parameter is statistically significant, and the answers were A, a large p-value, B,
number 11.
Number 11. Yep.
Yeah. Okay. So if you remember, statistical significance basically tells us 3 things that all. So statistical significance. You want a small standard error relative to your estimate. So the way we calculate that is typically we calculate what's called a t-statistic, where we take our, so for means, for example, we take our sample mean and we subtract some hypothetical value XO and divide by the standard error. And You see if the standard error is small, then the t-statistic is big. So we can have a small standard error, a big t-statistic, and then we convert that t-statistic into what's called a p-value by looking at the t-distribution, which looks like this. That's a terrible t-distribution. It looks like, that's better. We basically take our t-statistic, and the higher our t-statistic is, the farther away it is from the center. So as our t-statistic gets bigger, our p-value, which is the area in the tail, gets smaller and smaller and smaller. So those are our three indications. We want a small standard error, a big t-statistic, or a small p-value. And if all of these things are past some arbitrary threshold we set called the significance level, then we have statistical significance. And so if we go back to the question, a large p-value, we want a small p-value, so it can't be A. A small standard error, that seems right. Small t-statistic, we want a big t-statistic. And R squared is kind of a red herring. R squared is unrelated to statistical significance for a regression parameter. R squared is more about the goodness of fit of the entire regression. So we can throw that out. So the answer is B, a small standard error, because the other two, it says large p-value and small t-statistic, which are the opposite of what we want.
Awesome, awesome. Okay. I just have two more. One of them was it's impossible to calculate the slope in the regression model if blank.
Yeah, this one is kind of tricky. So if you remember our formula for slope, we have beta hat 1 equals this over this. Which is also just the covariance over the variance. Okay, and if we think about this formula is a fraction. All right, so there's one thing you can never do with fractions, right? So we can never have a 0 in the denominator, right? You can't divide by 0. So if this denominator is equal to 0, then we won't be able to calculate the value of our regression slope. Okay, and when will the denominator equal 0? Well, you can think about when will the variance of x equal 0, or when will the sum of squares of x equal 0. And basically that will happen when all x's are the same, right? If every x is 1, then x bar is going to be 1, and xi minus x bar is going to be 0 every single time, and so the sum of squares is going to be equal 0. There's no variance. So if all x's are the same, then the variance is going to be equal to 0, and we're not going to be able to calculate the slope. The slope is going to be undefined. And that actually carries over, if you remember like high school algebra, you might remember that the slope of a vertical line, the slope is undefined for a vertical line. And so when will the line of best fit be a vertical line? It's when every data point has the same x value. So that's the answer to that one. So you kind of have to, you can either just know that this is impossible to calculate if the variance is 0 or all x's are the same. That means the same thing, but that's the general idea. So this one would be, the answer would be B. There's no variation among the independent variable, which is just another way of saying all x's are the same.
Okay. Okay. I just got one more.
Sure.
It was the exogeneity and the endogeneity.
Endogenate.
Yeah. Which of the following terms is not synonymous with the others? And it had the, the
Question 12.
errors.
All right. So if you remember in our proof of unbiasedness, or really we relied on something called the zero conditional mean assumption when we were proving that the expected value of the sample slope is equal to the population slope. And we had, in order to prove that, we made this assumption that the expected value of the population error term conditional on our independent variable is 0. Or another way of writing this was that the covariance of the population error term and the independent variable is 0. Okay, and this is called our zero conditional mean assumption. And basically what we're assuming here is that there's no omitted variable bias. There's nothing that's correlated with both our independent and dependent variable that we're leaving out. Okay, and so it's called the zero conditional mean assumption. It means we're assuming there's no omitted variable bias, and another word for it is the exogeneity assumption. We're assuming that X is exogenous, meaning that, or basically, we're assuming the error term is exogenous, which means that there's nothing contained within the error term that is kind of tangled up within the relationship between X and Y. So the opposite of exogeneity, or the opposite of exogeneity, or the opposite of exogenous is what I meant to say, is endogeneity. If you have endogeneity, which means this assumption isn't being fulfilled, then you have a problem. So if you have omitted variables, you have endogeneity. So going back to here, exogeneity, this expression that, so this is, this one here is answer choice A. This here is answer choice B. Or sorry, this one's C. This is answer choice C. And this is answer choice D. This one is B. So we know that endogeneity is the wrong one out. We're not assuming endogeneity, we're assuming exogeneity. So that's just a kind of a terminology thing. So you can just know that no omitted variable bias, zero conditional mean, exogeneity, this expression, and this expression. Synonymous. So all of these things are basically mean the same thing. So the only one that's not in this list in the question is endogeneity. So we know the answer to that one is B.
Thank you. I appreciate the thing. I think I'm good. I think I'm ready.
Okay, awesome. If you have any other questions, just be sure to post them in the discussion board.
Oh, while I have you, actually.
Sure.
In the last question on the most recent problem set, in the problem set 3, it has the GPA equals, and it has the B1 class, B2 work, B3 study. It says, will this model produce valid results? Are any important assumptions being violated?
Ooh, yeah, that's a good question.
Yeah.
So this is something that we'll talk about a little bit more after the midterm. So if you remember our expression for when we have a multiple regression, I forgot the intercept. Wish I could just erase part of it, but I will. Okay, so we have our multiple regression. Okay, and we know that the expression for the slope beta hat 1 is basically this. Where this number is the residual from this regression. So we basically run a little side regression among our independent variables and get the residuals. And then we run a regression of those residuals on our dependent variable. I guess I can just give it a different. Okay, so if we regress these residuals on y, we'll get the same coefficient as in our multiple regression. Okay, but again, thinking about this formula, right, we know that this denominator can't be 0, right, because if it is 0, then you're dividing by 0 and you break the universe. Okay, so when will this, we need the sum of the residuals, squared residuals, from this side regression to equal 0. If for some we don't need that. If all of these residuals are 0, then this will be incalculable and the whole thing will break. Okay, so when will you have, and the sum of the residuals is only 0 if every single residual is 0. All right, so if you remember what residuals are in a bivariate regression, if we regress y on x, we draw the line, we have our scatter plot around it. If you remember, residuals are the distance between each data point and the regression line. Okay, so when will a regression have residuals that are all 0? Basically, the only time when that's the case is when there's an exact linear relationship between x and y, or in this case, between x and z.
So is that multi-collinearity?
It's called perfect collinearity. Multi-collinearity is when you get close to this.
Okay.
But if you have, so if x and z are perfectly linearly related, then you have what's called perfect collinearity.
And would there be perfect collinearity between work and?
Yeah, so in that question,
yeah.
So if you have perfect collinearity, if you can basically describe the relationship between any of the independent variables in a linear function, then the regression won't work. You need to drop one of them. And so if you remember in the question, we're asking basically someone to account for every single hour of their day, right? So we could write a function like this, work plus study plus sleep plus leisure plus other, right? That is always going to equal 24. And this is a linear relationship with no randomness, no error term, right? So these are all all of these variables included together are perfectly linear, perfectly collinear. Okay, so we can't include them all in our regression because those residuals in the side regression will be 0, and so we won't be able to calculate any of the slopes. So the solution is to just drop one of the variables, probably other, when you have perfect collinearity. You know, actually, if you try to do something in Stata like this, you know, let's generate x equals r normal, which is just, you know, making it normally distributed. And then we'll generate a variable that's perfectly collinear to x. Say z equals 3x plus 4. Sorry, did I call it something different? I just need to use a different syntax. Right? And then we try to regress beauty on x and z. Notice how it says x omitted because of collinearity. State is actually smart enough to know when you have collinearity, and so it'll drop one automatically if you try to do it. So yeah, so the answer to that question would just be, because these variables always add up to 24 for each individual, they're perfectly collinear, so we need to drop one, probably other.
Awesome, thanks. I think that's good now. My girlfriend here is bothering me to go get dinner, so
Okay, enjoy your dinner. Thanks for stopping by.
Thank you very much. I appreciate it.
Sure thing.
Have a good night.
Sure thing. And if anyone else has any other questions, you can put them in the chat, or you can get on your microphone and ask. That's fine if your mic's not working. You can just put a question in the chat. Yeah, go ahead. So the test is going to go up, I think, at midnight on Sunday, and you'll have until, so the 7th, and then it'll be active until 11:59 on the 13th. So basically pick any 2 hours the week of the 7th through the 13th to sit down and take the test. So it's, yeah. Any other questions that you have, or just the procedural one? Yeah, it's not going to require a lockdown browser. It's no, take your time. It's not going to require a lockdown browser. It's just in your browser, and you're allowed to use you know, you can use the textbook, you can use the lecture videos, you can look at the problem sets. The only thing you can't do is collaborate with other students. But other than that, you can use other materials. If you're using something besides the textbook or the lectures, like if you find a website or a paper, academic paper, or a different textbook, you have to cite it. But no, you won't require a lockdown browser. You just can't collaborate with other students. No, you won't have to use Stata. You should be able to, I think, I can actually look at it right now to see what the most math is. Yeah, so you won't need to do any calculations beyond something a four-function calculator would do. So you'll have to multiply, divide, add, subtract, but other than that, you won't have to do any other calculations. It's more conceptual. No, you won't really need to analyze any data set. Actually running regressions and doing analysis, that's the domain of the problem sets and the final paper. The exam is more to test your knowledge of the concepts at hand. Not at all, no problem. And again, if you haven't seen it, there's a, if you go to the assessments folder on the course page on Blackboard, there should be a fall 2020 midterm visible. This is the midterm I gave last semester. That's going to be a fairly decent approximation of what the test is going to be like. If you want to run through that and try taking it under time constraints, I think that's a great way to study. Sure thing. Can you give an example of a like a function or a proof we've done where you understand the math but not why we made a certain assumption? No, it's fine. I think we can kind of like summarize, so we started with thinking about, I guess, with functions. Our goal at the very beginning was just to, answer the question, how are these two variables related? If X moves, what's going to happen to Y? Is Y going to move with it? Basically every question in economics, or not every, most questions in economics can boil down to just asking how are these two variables related. So if you raise the minimum wage, how much is employment going to fall, right? And so our first tool for doing that was covariance. And the issue with covariance was that it was scale dependent. basically it couldn't tell you, it could tell you, you know, the direction that X and Y are related. So if it's positive, that means when X goes up, Y goes up too. But it can't really tell you anything beyond that. Okay, so then we moved on to correlation, which was a little better. Correlation, if it's close to 1, that means X and Y are really closely related. And if correlation is near 0, that means that they're not related at all. Okay, but a problem with correlation was that if you have, you know, 2 scatter plots, one that looked like this, like a really steep like this, and then another one that looked like this, where it's more flat. Okay, it's possible that these two have the same correlation. Like both of these could have a correlation of like 0.8 and 0.8. So correlation can't tell us the kind of slope of the relationship, or kind of the magnitude, I think is a better word, of the relationship. So correlation says, okay, if X goes up, then Y definitely goes up, but is it going to go up a lot? Is it going to go up just a little bit? And so that's what motivated us to get into regression. Or like, yeah, regression, starting with bivariate regression. All right, and there, you know, our goal was to take these scatter plots and fitting a line through it. And the slope of this line should tell us the size of the relationship. So these two scatter plots, right, they have the same correlation, but they have different regression lines, right? This one's really steep, and this one's more flat. Okay. But then we could get into, you know, well, is this regression got you know, indicative of an underlying relationship, or do we just have a weird sample? Right? It's possible that we just got a weird sample of individuals when we constructed our scatter plot here, and there actually is no relationship between X and Y, which is what brought us into unbiasedness and variance. You know, we showed two in the lecture video for that week. We talk about two scatter plots with different standard errors, which can help you kind of visualize why we're doing this. But basically, we want to do hypothesis testing on these regression slopes. Okay, but then we came up with an issue of, well, these scatter plots, you know, are great and all, but they might not actually be telling us about the causal relationship between these variables, right? They're really good at giving us the correlation. We can tell you everything about the correlation between X and Y. We can give you a predicted value for X or for Y based on any X value. We can tell you how likely is it that we observe this slope given the variance and the residual terms, right? But, you know, all of that doesn't really matter if we're interested in causality, which is what motivated us to get into the last topic of this semester, which was multiple regression. Where we really want to start trying to combat omitted variable bias, right? That was our main reason for going into multiple regression. You know, we talked about how, you know, if you run the regression of income on years of education, we can learn, you'll probably get an estimate of the slope that's positive and statistically significant. But that's probably not the real effect of education on income, because we have omitted variable bias. Okay, so the solution then was to, instead of using bivariate regression, to use multiple regression. So that's the motivation behind that. So I think that kind of shows the progression from covariance all the way up to multiple regression. There's something that we add at each step in that chain that's valuable to us. And after the midterm, we'll talk about, even more ways that we can kind of expand it. Mainly, our two enemies after the midterm are going to be unobservables. Oops. Right, variables that we can't observe but are omitted, right? So we can't just plug them into our multiple regression and control for them. We need to find some other ways. And simultaneity bias. When two variables are causally affecting each other, and how can we untangle that? So that's going to be where we're headed after the midterm. But we can't use covariance because it's scale dependent, so we learned about correlation. Correlation can't tell us the kind of actual relationship between the two variables. It can only tell us how weak or strong it is. Regression, or bivariate regression, is good, but it has problems with omitted variable bias. Multiple regression is even better, but there's issues of unobservables and simultaneity bias, and so we'll just go from there. Sure. Awesome. Anything else you'd like me to rant about? Discuss? Oops, sorry. Okay, awesome. Yeah, so if you have any other questions, that's not a problem at all. Don't worry about that. If you have any other questions before the midterm, just you can post in the discussion board, and I'll do my best to answer you. Let's see, has anyone else joined? All right, yep, and so if you're, if this has been recorded, so if you're watching this and it's before you take the midterm, you can also post in the discussion board, and I'll happily answer your question. If there are enough, if there's just an outflow of questions between now and Sunday, maybe I'll make another video. But thank you to those who stopped by. Thank you to those who asked questions. Good luck studying.